Hey y'all, so today we're going to continue on with our unit on logarithms, and eventually we'll want to get to a point where we're able to solve equations that involve exponential and logarithmic functions, and we're going to use logarithms to do that. But before we really get into the solving aspect, we need to know how to properly manipulate logarithmic expressions, and we're going to do that by taking advantage of some different properties that logarithms have. So the first thing that I'm going to show you is how to change the base of a logarithm. So in general, let's say you have some log with a base, and let's say this base was like 10, for instance. And for whatever reason, you might find yourself wanting to change what this number is. What we'll see later on is it can be helpful to have all of your logarithms in a given equation with the same base. So if there's an occasion where like you have a log base 2 and a log base 3 in the same equation, to be able to simplify it, it would be helpful to know how to change the base of one of those logarithms. So it's a pretty straightforward process here. This is going to equal log of whatever your argument is over log of the base. So that base becomes the argument of the denominator. Now, it may look like, okay, well, I just changed this to base 10. You could actually change this to any base. So this could be 10. You could just write it like that. It could be 2. You could change it to base 2. You could change it to base e and have like a natural log. You can really change this to any base you want. So I'm just going to put like a little star here and say that star can be any base. Now, when I say any base, there are obviously some restrictions to what the base has or can be. We talked about that last time, that this base can't be negative and it can't be 1 either, or 0 for that matter. So it's got to be positive, and the only positive number it can't really be is 1. So so that's how we're going to go ahead and change the base. So let's go through a couple of just logarithms you should know what the value is going to end up being just by looking at it. We'll come back to this log non-positives, but let's start with the log of 1. Let's say you want to take log any base, let's say base 10 of 1. So the question here is like b to what power is 1? And that is always going to equal 0 because anything to the 0th power is 1. Similarly, if you want to say, okay, well, log base b of b, so let's say it's like log base 2 of 2, if these numbers are the same, you're saying, in the example of 2, 2 to what power is 2, and that'll always be 1. So if this number inside here is the base, then it'll always equal 1. If the argument here is 1, the logarithm, regardless of the base, can equal 0, assuming the base is a valid number for logarithms. But let's say that number inside there is like a negative number or 0. So if that number in there is less than or equal to 0, meaning it's a negative or 0, non-positive, kind of weird way to put that, but I don't want to just say negatives because I want to include 0 as well. And that's going to be undefined, because if you have, let's say you have like log base 2 of negative 5. Well, 2 to what power is negative 5? There is no real number that will make that happen. So in this case, whenever you have a negative number or a 0 on the inside of those parentheses, you're going to say it's undefined. There's no value. So these three are just ones that you want to be aware of. These are going to pop up from time to time. But let's take a closer look at some of the other properties and how you might be able to use them to simplify or to expand logarithmic expressions. So logarithms have very similar properties to exponential expressions, and what I want to show you is how similar they are. So in previous years, you've probably talked about the different exponent properties in Algebra 2 and Algebra 1. But what I want to show you is like, what is the logarithm counterpart to that property? So for example, the product property, which states that if you've got some base to 1 power and you want to multiply that by a base, the same base to a different power, you are going to add those powers to simplify that, right? Similarly, for logarithms, let's say you have 2 logarithms with the same base. So let's say log base b of x plus log base b of y. I want you to think about this, that remember that logarithms are the inverse of exponential functions. So kind of let's see how this is set up, where we've got the base and we've got two different logarithms, and we're adding them. So when you think about, well, like, what do you think is going to happen here? What is this going to equal? And so what this actually equals is log base b of x times y. So notice you're kind of going backwards from, instead of going from multiplication to addition, you're going from addition to multiplication. So that's the product property for exponents and for logarithms. We have a similar quotient property, which is really essentially the same property, just involving some reciprocal action here. So let's say we've got b to the x divided by b to the y. You may recall that when you're dividing different powers that have the same base, you subtract those exponents to get your result. So similarly, we're going to have a very, very similar statement over here, where we've got log base b of x minus log base b of y. And if we wanted to combine those, we would combine them with division. So we've got, this would equal log base b of x over y. We've also got the power properties. Now for exponents, when you raise a power to another power, to simplify that, you just want to multiply your powers there. So you get x times y. So like for instance, if you have 3 squared cubed, that would be equivalent to saying 3 to the power of 2 times 3, which would be 6, so 3 to the 6th power. Since logarithms are powers, you're going to find that the logarithms are going to work similarly, just kind of almost like backwards. So let's say we've got something like log base b of x to the yth power. What would that be? Well, what would happen is you could take this exponent and actually move it to be a coefficient of the logarithm. And I want to show you, I want to go into a little bit more detail why that is, why this particular property works. I think it's worth examining a little closer, because I don't think that this one is as intuitive as the previous two properties. So let's take a quick look at that. So let's say I wanted to show that, let's say we had log base 2 of x cubed, and I want to show that that is actually equivalent to 3 times log base 2 of x. So I took the exponent on the inside of that argument and just kind of threw it over here as a coefficient. So why does that work? Well, let's say when we write log base 2 of x cubed, well, we can rewrite this a little bit, because let's think about what this actually means. X cubed is really log base 2 of x times x times x, right? It's just x times itself 3 times. And then we can take a quick look back at our product property and say, okay, well, if I have log base b of x times y, then that should be equivalent, based on this other exponent property, to log base b of x plus log base b of y. Right, so I can basically separate these factors into two different logarithms by changing over to addition here. So if these two numbers are the same, that doesn't really affect the validity of this property. So if I'm multiplying 3 different x's in there, I can rewrite that using that product property as log base 2 of x plus log base 2 of x plus log base 2 of x. So I've got 3 of them, and whenever you are doing this repeated addition, that's what we call multiplication, right? If I'm adding the same thing 3 times, then that's the same as taking it once and multiplying it by 3. So as you can see, the proof here is pretty short. Hopefully that can shed some light on why this is true. And really it's just, this particular property, it really isn't necessary as like a separate property. It's handy to know, but it's really just an extension of that product property. So next up, we want to look at this, what I call inverse property. This is going to be really helpful for solving equations, because what this will allow us to do is to sort of undo what's being done. And that's what we do a lot when we solve equations. Like if I have an equation like 2x equals 10, a 2 times x, what I want to do is do the inverse of multiplication, which is division, and undo that times 2 to figure out my solution, right? Similarly, if I've got sine of x equals, let's say, root 3 over 2, and I want to figure out what x is, I would need to do the inverse to both sides and say x equals the inverse sine of root 3 over 2. So this method of solving is what we do all the time, right? So we want to know how does this work for exponential and logarithms. This little technique will be useful if your unknown is inside the argument, meaning like you're saying 2 to the x power if you want to isolate an exponent, or if your x is inside the logarithm and you want to isolate that value. So these inverse properties are basically going to show you how to cancel out each individual function. So for the exponent, let's say we had b to the power of log base b of x. Okay, so if I have, in other words, if I have log base b of x, forget the b for a minute, this first one. If I just had log base b of x and I want to say, okay, well, how do I make this equal x? Let's say I want to manipulate it somehow so that this thing just equals x. I want to get rid of the log base b. To do that, I would need to have this be a power with a base that's b. In other words, these bases need to be the same. Because this is saying, you know, if I want to evaluate this, this is saying b to what power, right? B to what power is x. So if that is my power, then this is just going to equal x. Okay, so this is going to be how you cancel that out. Similarly, on the logarithm side, I know, logarithms and exponentials are kind of working both ways here, but let's say I had log base b of b to the x. Now this one's a little bit easier to see why this equals x. We can really just go back to this last property, right? Like if I were to bring the x over to be a coefficient, like I just showed you up here with the power property, you have x times log base b of b. And one of the first little logarithms that we went over that you should just kind of know is that when you have log base b of b, that equals 1. So if I've got x times log base b of b, I've got x times 1, which is x. So if you're trying to isolate an x that's in an exponent, you want to take the log of both sides of your equation. Over here, if you've got log base b and I want to get rid of that, then you want to raise both sides of the equation to a power. And we're going to have a lot more practice using these inverse properties as we move in the coming days when we start solving more and more equations. We'll solve a few today, but for the most part, I want to just play with these properties. There's one more property left, and that's the one-to-one property. So let's talk about that for a moment here. So the one-to-one property for both multiplication and, for exponents and logarithms is an if-then statement. So basically, if your equation meets some condition, then we can make a conclusion from that. So for the exponent side, if we have b to the x equals b to the y, if this is our equation, then we can conclude that x equals y. Okay, we can get rid of the base, we can drop the bases and just set the exponents equal to each other as long as the bases are equal. On the logarithm side, we have a very similar property that says if log base b of x equals, am I going to run out of room here? Write a little smaller, log base b of y. So in other words, you have two equal logarithms with the same base, then that means that these arguments must be the same. So this will be nice, like if you've got an equation, like let's say you've got like log base 2 of x plus 1 equals log base 2 of 3, you could just drop those logarithms and just say x plus 1 equals 3 and solve from there. So that's kind of the idea of when you would use that. So that's pretty much all the properties y'all need to know. At this point, let's work out a few examples here so you can kind of get a feel for what kinds of questions I'm going to be asking you. in terms of trying to either condense or expand a logarithmic expression, and then we'll start get our toes a little wet in the solving equations portion. So let's look at some logarithmic expressions here and say, okay, well, let's expand them as much as we can. So if I'm looking at this log base 3 of 4x, I see I've got 4 times x. So I'm going to use that power property to rewrite this and try to separate these factors out. So I would say that this equals log base 3 of 4 plus log base 3 of x. And so that's as expanded as we can get. We've got no more factors in either one of these, so we're essentially done here. You do want to look for opportunities to simplify when you can. So like if 4 was a power of 3, like let's say this was 9x momentarily, you would get log base 3 of 9, which would equal 2. So you could rewrite this as 2 plus whatever, right? Now, 4 is not a power of 3, or at least not an even power. It's going to be an irrational power. So we're just going to leave it like this. Log base 3 of 4 plus log base 3 of x, and that would be our expansion. If you've got something with the power here, be careful, okay? Don't put the 4 out over here first because the 3 is not being raised to the 4th power, just the x is. So really the proper way to do this is going to be to split it up first and then take care of the exponent. So let's say I've got natural log of 3 plus natural log of x to the 4th. So split it up just like what we did in this one. But then we also want to try to take this power out. And this is just, what we're doing here is just kind of practicing manipulating these expressions. So we're not solving for anything yet. We're just kind of getting a feel for what we're allowed to do in terms of rewriting expressions. So that when we do get to the equations, we're a little bit more familiar with what the rules are, so to speak. So the last thing we want to do here is we want to move this 4 out over here. Again, right now this seems like just sort of like a, why would we even want to do that kind of step, but you'll see later on where knowing how to do that will pay off. Now, the multiplication and the power rules, those are going to be the simpler problems. It gets a little bit trickier when you have division in your argument, only because you have to be careful about separating out each of the factors, especially when you have multiple factors in the denominator like this one, number 4. So let's look at number 3 first. What I would recommend you do is just like look at each factor individually here. I like to kind of do it all at once. I know different people will have different approaches to this. This is just kind of the way how I see it, which is I see that I've got a 6, x squared, and a y to the 4th. Those are my different factors. And any factor that's in the numerator, when I split it up like this, is going to be positive. Any factor that's in the denominator is going to end up being negative. So I'm going to rewrite this as log of 6 plus log of x squared minus log of y to the 4th. Now I still have to take care of those exponents like I did in the last one, but this is going to be the first step here. To follow that up, we've got log 6. We're going to bring down this exponent to 2 out to be a coefficient of the logarithm. So you get 2 times log of x. And then finally, minus 4 times log of y. And that would be as expanded as you could get. You could say like plus log x, but that really is not necessary. So there you go. That would be how you do that one. Now you just want to be careful on number 4 is you're not going to say log base 2 of x minus log base 2 of 3 plus log base 2 of y. It might be a case where you say minus and then put all this stuff in parentheses, but I think it's easier to just kind of take this factor approach where you just circle the factors, and any of the factors that are on top are going to be positive, the ones on the bottom are going to be negative. So we've got log base 2 of x minus log base 2 of 3, getting a little sloppy with the parentheses there, minus log base 2 of y. what I was saying before about minus and parentheses, it could be that you might see this, and I'll write this briefly, but I kind of want to erase it because I kind of like this other method better. But you could go like this: log base 2 of x minus, and then do like a bracket parenthesis here, log base 2 of 3 plus log base 2 of y. But I think this just kind of confuses the issue, quite honestly, because then you just distribute that minus anyway, and you'd end up here. But I've seen this a lot in different textbooks and whatnot. So I kind of like just going straight to it. That way you don't have to worry about all the distributing and all that stuff. Just that, hey, if you've got a factor on top, it's going to be a positive logarithm. The ones on the bottom will be negative. So really, that's most of what you're going to see in terms of trying to expand logarithms. Really, the only other note I wanted to make is when you start seeing these square roots, you have to know what square root actually means to really knock this one out. Now you might look at this and say, okay, well I've got two factors here, and so I could rewrite this as log base 7 of 5 plus log base 7 of root x. And you wouldn't be wrong. Like that's perfectly fine, but we can actually go a step further if we know, and maybe I'll make a little note out here, that the square root of x is actually equal to x to the 1/2. That's what square root of x actually means. These are equivalent. Similarly, and we'll see this in number 6, the cube root of x is equal to x to the 1/3. The fourth root of x is equal to x to the 1/4, and so on. So that'll come into play here on a couple of these. So if this is actually x to the 1/2, then we can use that power property to take this one step further and move this out over here. Now that's going to be pretty helpful if we've got it like an equation where this is equal to something. If we want to like undo the logarithm and then eventually we've got to undo that, this can be a way so that you don't have to worry about that. You basically get rid of the square root before you even do anything in the solving department. So I can finally write this as log base 7 of 5 plus 1/2 log base 7 of x. So it's good to know that, just so don't get thrown off when you see the square root. Just know what that really means, which is just x to the 1/2. Now number 6 has kind of a lot going on here. So let's take a closer look at this one. We've got a cube root of a bunch of stuff. So you actually got like this whole thing. I'm going to rewrite that first. I don't like having that cube root in there. Instead, I'm going to write that as x squared y, all that to the 1/3 power. So don't be, this cube root is over all of this. So we have to really deal with that first before we can start separating things out. So I'm going to move this 1/3 out to the front before I actually start separating anything else. So so now I've got 1/3 times this, right? So that's 1/3 times the rest of the expression. So when I expand this out, I got to make sure that it's 1/3 times the whole thing, okay, and not just whatever I happen to write first. So let's see what happens here. We get 1/3 times log base 5 of this x squared plus log base 5 of y. Notice I'm multiplying the whole thing by 1/3, not just this first one. The last thing here to do would be to move the 2 over here. And so I get 1/3 times 2 log base 5 of x plus log base 5 of y. You can pretty much be done here, although you could multiply the 1/3 back in if you want to. You don't have to do that, but if you choose to, you'd get 2/3 times log base 5x plus 1/3 log base 5 of y. I don't know which one you're going to see, but if you can get this far, it should be pretty obvious how to take it to the next step if you needed to for some reason. Here's 6 examples on how to expand the logarithms, how to write them with as many logs as you can. What I want to show you next is how to condense them, so kind of how to go backwards. If I have an expression like this, how do I get back home? Most of the time, you are not going to be doing a whole lot of expanding when you solve. Most of the time when you're solving, you're trying to reduce and simplify, so you're kind of wanting to go backwards. Let's go over how to do that. All right, so here's a few problems where we want to condense the logarithms, try to write it in as few number of logarithms as possible. Really, our goal here is to write it as a single logarithm. So if you've got two logarithms with the same base and you're trying to subtract, you can just use that that quotient property just straight away here. So this will equal log base 4 of 7/10. So you want to be careful here. Remember, the goal is to reduce the number of logarithms that you're writing. A lot of times I'll see students who are doing this for the first time just kind of confuse what the property is and try to write this as log base 4 of 7 divided by log base 4 of 10. But you can't just change this from subtraction to division, or else you're changing the value of the expression. You have to make sure that when you're trying to condense the logarithm, you're actually doing that, and you're reducing the number of logarithms to 1, and you're just dividing the arguments, not the overall expression. So that's how you'd write this as a single logarithm. Number 2 is similar. We'll use the product property here because we've got addition instead of subtraction. The other thing to notice here is that we've got this coefficient of 2 on the log x. So we're going to take care of that first and rewrite this as log of x squared plus log of 11. Kind of got a little sloppy with my parentheses again. It's kind of easy to forget them. A lot of textbooks won't even use them, but I really do like having them because I think it really establishes and makes it clear that you're talking about a function. And also, when you have something like log x squared, particularly, it's good to know that the squared is on the inside of the argument rather than the outside, because that would kind of change what's going on here. Although, quite often I do just, see textbooks without the parentheses here, log x squared, and I guess you're just supposed to assume the squared's on the inside. But if you include the parentheses, you can sort of get rid of that ambiguity. So now we can combine these as a single logarithm. We get log of x squared times 11. Now this isn't a very conventional way of writing this product out. Typically, you'll write the coefficient before the variable, or your constant before the variable. So let's just rewrite that, make it look a little cleaner. And there you go. It's not wrong if you write it like this, but this just looks a little nicer, I think. So this doesn't really get much more complicated other than just like making sure you're putting the exponents in the right place and making sure you're either multiplying or dividing depending on addition or subtraction. But when you have multiple terms like this, you kind of want to think back to how we expanded the logarithms, and that was any factor that was in the numerator ended up being a positive part of the expression, where any of these in the denominator ended up turning into a negative part of the expression. So to kind of play that backwards, if I see a positive log here, and when I go to basically what's going to end up happening is I'm going to write this as a natural log of, and then a big fraction. And any of these that are positive, this thing is going to end up at the numerator. Any one that are negative are going to end up in the denominator. Before I try to combine everything, let's take care of these coefficients and rewrite them as exponents. So that'd be natural log of x to the 5th minus natural log of y to the 7th plus natural log of z to the 4th. And so now we got rid of all the coefficients. Now we can start to combine this stuff. And so this is just going to turn into a big fraction, natural log of, and we're just going to decide like what goes on top, what goes on the bottom, and that's just going to the way we're going to know that is if it's positive or negative. So if it's positive, like this first one, there's no negative sign in front of it. This x to the 5th should be in the numerator. Oh, that's not a 2. That should be a 5. So we got x to the 5th, and then minus. So this is a minus. This is a negative term. And so y to the 7th is going to end up on the denominator. And then we've got one more positive one. Z to the 4th should end up in the numerator. So now we've written this as just a single logarithm. So this is going to be what you use a lot of times when you're solving equations. So I just want to show you just a couple equations. I don't want to get too heavy into the equations yet. I know we solved a couple of different sort of simple equations in the previous lesson. I do want to kind of kind of dive in a little bit into equations today, not a lot, but just to kind of get you starting to think in terms of how to use these properties. So most of the equations you're going to be solving today are just going to be direct applications of these properties. So let's just look at a few of them, and that's going to be pretty much it for today. So let's take a look. All right, so I just want to show you just a couple of ways on how you can use some of these properties. So let's say you've got an equation where you've got the exact same logarithm on both sides. We've got log base Euler's number, otherwise known as the natural log. Anytime you've got the same based logarithm on both sides, you can use that one-to-one property and just sort of cancel out the logarithms. Now, the way that really, what's really happening here is we are raising both of these sides as a power of e, or Euler's number, and then we can use the inverse property. Let me kind of scoot back here and say that, if you've got, a base raised to log base with the same base, then you're just left with the argument. And this inverse property is how you cancel out whatever you have. That leads to the one-to-one property, which says if you've got two bases which are the same, then you could just drop the base, so to speak, and set the arguments equal to each other. So this one's, I think, pretty intuitive. I don't know that you really need to write this. I know that is one way to kind of show why that is, but we can just say that we're applying the one-to-one property rather than the inverse property here. And that one-to-one property is sort of just it occurs because of the inverse property. So anyway, once you drop those, you can solve this just like a regular old linear equation. I'm not going to get all into that. I assume you guys know how to solve linear equations at this point. You've been dealing with those since at least Algebra 1, if not earlier. So let's see, 5 plus 7 is 12. So you get 3x equals 12, so x is 4. Now, before we go any further, we need to make sure that this is actually a valid answer. Remember that you can't take the logarithm of 0 or a negative number. So I just want to cross-check this real quick and make sure that doesn't cause any problems. So like if I plug in 4 here, 4 plus 5 is 9, so that's safe. Over here, 16 minus 7 is 9. I'm kind of expecting those to be the same. So I do get a positive number in all the logarithms, so I'm safe. I'm good. That means this is going to be my solution. But I do need to make that check anytime I try to invert these things. Okay, so here's another one. Notice here we don't have a logarithm on both sides. We can't use that one-to-one property here. But what we can do is use the quotient property to try to get this down to just a single logarithm, and then we can rewrite it as an exponential equation like we did last time. So let's use the quotient property here and rewrite this as log base 5 of a plus 3 over a minus 1 equals 1. And you might think, okay, well, I still can't really solve that with the one-to-one property like we did up here because I only have the log on one side. So we need to think about how do we rewrite this as an exponential equation like we did in the previous day. So remember that a logarithm is just a power. That's all it is. And so what this is really saying is that 5, okay, to the first power, that's what the logarithm is, it's just a power. So 5 to the first power equals this. All right, so I'm going to rewrite this as 5 to the first power equals this. And all of a sudden, this becomes a much more approachable problem. 5 to the first power is just 5. Anything to the first power is just itself. We can now multiply the a minus 1 to both sides so that we get rid of our fractions. Okay, and now we've broken this down. Now we've just got another linear equation we got to solve. So again, I'm going to kind of run through this. I don't think we need to spend too much time on how to solve linear equations. So as I go through these steps, just subtract a on both sides, gives me 4a minus 5 equals 3. Now I've got a two-step equation here. Add 5 will give me 8, and then divide by 4, we get 2. So I get a equals 2. Again, I do need to double check that, make sure 2 doesn't cause any issues in the domain of these logarithmic functions. So if I plug in 2 here, 2 plus 3 is 5, so that checks out. 2 minus 1 is 1, so that's good too. Remember that what's going to prevent it from being an actual solution is if you plug it in somewhere and you get a negative number or you get a 0, because you can't take the logarithm of either of those two things. They're outside the domain of the function. All right, let's look at one last one. So the previous one we used the quotient property. Here we're going to use the product property. So we've got a very similar setup here, except instead of dividing, we're going to be multiplying. So I'm going to rewrite this as log of, and this is, okay, so log of 5x times x minus 1. So I do need to multiply this out, okay, and so that gives me log of 5x squared minus 5x equals 2. You kind of hope that you have the same log on both sides because, you know, a lot of times it probably is just easier that way, that you could drop the logarithms using the one-to-one property like we did in the first problem. But this is a little bit more like number 2 where you don't have the ability to do that, so you've got to rewrite this as an exponential equation. The base here isn't written, so it's assumed to be 10. It's sort of our favorite number. So that's a common logarithm. So 10 to the second power equals this. So 10 squared equals 5x squared minus 5x. Now 10 squared is 100, and it looks like, fortunately or unfortunately, depending on your perspective, it looks like we've got a quadratic here. Okay, so not a linear equation. So I'm going to put this into standard form. Which means I want it equal to 0, so I can utilize either the what I really would like to do is to factor this. I could use the quadratic formula, but factoring is just so much easier when you can, and so much less tedious to do it that way. The first thing I'm noticing here is I've got a factor of 5 here, so let's just divide that out first. Divide both sides by 5, and let's make these numbers a little bit smaller here. 0 divided by 5 is 0. That's kind of why we're doing that. So x squared minus x minus 20. And so I'm going to go ahead and factor this. And I'm going to assume you know how to factor, but just real briefly, when that a value is 1 here, you're looking for two numbers that multiply to give you negative 20 and add up to negative 1. And that would be negative 5 and positive 4. So my factors are x minus 5 times x plus 4. Now we can use the zero product property, which states that at least one of these things has got to be 0. So either x minus 5 equals 0 or x plus 4 equals 0. That gives us x equals 5 or x equals negative 4. Now before you claim both of these are solutions, we do, just like on the other problems, need to double check and make sure that's actually true. So let's try 5. Let's just like plug in 5 real quick. So 5 times 5 is 25. That's good to go. 5 minus 1 is 4. Both positive, no problems. So we've checked out, yeah, x equals 5 works. Negative 4. Now, this should kind of give you cause for concern, the fact that it's negative, although not necessarily. Like if I have something like log of negative x and my solution is negative 4, that's not going to cause any problems, right? Because negative 4 would be positive 4. So we don't have that in this problem, but just a word of warning that just because your solution is negative does not necessarily mean it's going to be a bad solution. So let's plug that back in. We plug in negative 4, and right away we get 5 times negative 4 is negative 20. So we get this undefined logarithm, which kind of screws everything up. So this is what we're going to call an extraneous solution. It's actually not a solution. It just, because of the way we're solving this problem, it does pop up. But this kind of shows you that, hey, you do need to be checking your solutions and make sure they're valid within the domain of the log function in your equation. So that's pretty much it for today. We will dive a lot deeper into solving equations, and that's really what we're going to focus on from here on out for the rest of the unit, is how to solve more and more complicated equations.